with dessert.
Uh-oh. All right. Now we're going to move on to the next topic. So far we've discussed derivatives of functions using the chain rule and derivatives of trig functions, the regular functions and trig functions, or transcendentals. Now we're going to go one step further. We're going to go backwards. Inverse functions. Let's review this inverse functions from algebra. If f of x was our function, let's say 3x plus 2, the inverse of that function would be designated with this -1 exponent. Now, to find the inverse, it's only 2 steps. First step, you switch x and y. And then the second step is you solve for y. That y will become your inverse. So for this example here, we have y equals 3x plus 2. That's our function. First step, we switch x and y. Now we solve for y. Subtract 2 from both sides. We have x minus 2 equals 3y. And then divide by 3. So my inverse is x minus 2 over 3. So I'm going from here to here. All right, so that's just simply the mechanics of it. Actually, while we're here, might as well do this part that's going to be needed for the end part of this section. What if my function was e to the power x? What's the inverse of that function?
The natural law?
How do you mean?
It would be log. No. Wait.
No, to what? Remember, let's follow the steps. So first step, we switch x and y. Now, second step, we have to solve for y. Since y is the exponent, how do we get rid of the exponent? We take the logarithm of both sides. Log base, or whatever this base is. Since it's e, remember, log base e is ln. It's a natural log. So we're taking the ln of both sides. That's one property. Another property that we have of logarithms or logarithmic functions whenever the bases are the same, they cancel out. So the exponent comes out in front. Log base a of a is 1. So the answer is x. So that means the exponent comes out in front. The ln of e is 1. So the inverse of y is equal to the ln of x. And vice versa. If y equals ln x, the inverse is e to the power x. Okay, so that's the mechanics of finding the inverse function. How do we test to make sure they're valid inverse functions? To test if anybody remember how to test that? We use the composition of functions. More so, we use the Fogg and Goff method. Do you remember what that meant? A composition, the reason they call it Fogg, because these are two functions taken, not multi into, it's one inside the other. The way this is read, the reason they call it Fogg, it says f of g. Goff is g of f. Now, why is the word of important? Because how do you read this? How would you read that? This is f of x. So whatever is after the of is what's inside the parentheses. So what this says, it's a composition of functions. Now, if two functions are inverses of each other, then it doesn't matter which way we perform the composition. So it's the f of f inverse of x, or the f inverse of f of x. They both have to equal the same thing. They both have to equal x. And to be safe, we usually take both of these when we do a test. But we get lazy, we only do one and say it's 50-50 chance the other one works. So have it your way. So let's look at our examples that we had earlier. If f of x was 3x plus 2, the inverse we figured out was x minus 2 over 3. So the the f of f inverse. What this thing tells us is this. The inverse function, anywhere I see an x in the original function, I put the inverse function. So what it's telling us is I have 3 f inverse of x plus 2. What is the f inverse of x? X minus 2 over 3 plus 2. Now let's work it out. First thing we do, cancel. The 3's cancel. So we have x minus 2 plus 2. Negative 2 plus 2. So we have x. So since that works, we know that that is a true inverse of this function. And the other way, we would take this function and plug it in place of x in the other one. That is what this would have been done.
So is it the inverse of the inverse?
No, there's only one inverse. It's just that this is just a test. The composition of f of inverse or f inverse of f. The inverse is the first process you do. This is just the test of it. We use the composition of functions.
So we're not inverting that inversion.
No.
Okay,
We're just checking to see, and just this is, if I take this function, the inverse function, plug it inside here, will it get rid of everything? Yes, it does. And the same thing here. Well, let's switch it out. So if we did the f inverse of f, so in my f inverse function, anywhere I see an x, I put an f of x. So I have f of x minus 2 over 3. That's what that says. F of x is 3x plus 2 minus 2 over 3. Two minus 2 cancels. The 3's cancel, and we're left with x, which is what our test was all about. All right, so now how does this help us? Because now we have to be able to take derivatives of inverse functions. Because if we have a function, we can take the derivative of it. What are the conditions? When can that happen? When can you take the derivative of a function? What are the conditions that have to be true? Has to be continuous, right? So if the function is continuous, that means it's differentiable. So if a function is continuous, we also know so is its inverse. If f is continuous, then f inverse is also continuous. Because they both meet the concept of continuity for differentiability, then f inverse has a derivative also. And that's what we're going to try to find here. Oh, real quick. The last example that we had 3x plus 2. The inverse was x minus 2 over 3. True? These are both linear equations, aren't they? What's the slope of this one? What's the slope of this one? Very good. So it's 1/3 x minus 2/3. And this is not a unique case. The slope of any function and the slope of its inverses is always symmetric about the line y equals x. They're always reciprocal of each other. That's important because that's going to help us when we do the derivative of it. All right, let's see if we have some example here. So the derivative of our function, let's just derive this thing. Because remember, the derivative is a slope, right? It's best if now if we look at picture. So we have 2 points. A, f of A. And here's at line y equals b. So the other one will be at b f of b. They'll be on the other side of that line. Remember, inverses. So these are 2 points that are on the graph that are inverses of each other. So the derivative of the inverse would be the same as what? Remember, this is a slope. The derivative represents a slope. So that's the slope. Then that has to be the inverse of the derivative of the first value. Let's call this one A, and let's call this one B. This is also the slope. Is this a true statement? We just talked about it.
Yes.
The slope of the function is 3. The slope of the inverse is negative. So f prime is 3. F in the prime of inverse is 1 over 3. Or 1 over f prime. That's the connection we're trying to make here. So what we have right now is the derivative of our value at b, the second point, is 1 over the derivative of the first point. So what exactly is this first point? Well, that's the derivative of the value of the inverse. So our formula then the formula we'll be using from here on out for the derivatives of inverse functions will simply be 1 over the derivative of the original function of the inverse function. This is the formula we'll be using from here on out. Looking at the proof here. Why? Because we have two functions, f of x and f inverse of x. What do we know about those two? If we do the composite of the two functions, what does that equal? X. Now, if we take the derivative of both of those, we take the derivative, this side here, we have to use which process? So the derivative of x is 1. Well, how do we find the derivative of this side? This is a function within a function, so we use which rule? Right. We have to use, remember, the chain rule applies whenever you have a function within a function. And remember what that one was. It was f prime of g of x times the derivative of g of x. So inside here, what do we have? So we have f prime of f inverse of x times the derivative of the inside. So the derivative of the inverse can be written as dy inverse over dx we want to find the derivative. This is the derivative of the inverse function. So we divide both sides by so that gives us our derivative of the inverse. Oops, sorry. I hate that I can't extend this one. So this is the same thing we have up there. The derivative of the inverse is equal to 1 over the derivative of the function composite with the inverse function. Now, the reason why we do this is because now you don't have to go through the whole process whenever you do derivatives of these things. You just have to plug and play in this function. All you have to do is find the f inverse, f prime, and there you have it. And plug them together. The function x squared, when x is greater than 0, what is its inverse? What is its inverse?
Square root.
Right, so we start off with switch X and Y. Nope. Switch X and Y first. Then we square root both sides. Actually, it's plus or minus square root. So Y is equal to the Y inverse is equal to the plus or minus square root of X.
Professor, would it still be plus or minus if x is greater than 0?
Ah, very good. I would say, but we've limited our domain to that. So now our inverse, good catch. We're only dealing with the positive x's. So now we know our f of x. We know our inverse. What are other derivatives? What is f prime of x? And what is the derivative of the inverse? So what's the derivative of fx?
2x.
To find the derivative of the inverse, we use our formula. So f prime is 2x. Now in place of x, we put the inverse function. What's the inverse function? Square root of x. And there's your inverse. There's your derivative. F prime of this is square root of x. F prime was 2 of x, so it's 2 square root of x. Let's look at another example.
Really just setting all this up and then putting it all.
Plug and play. Yeah, it's just once we set up, once we have our original function, find the inverse, take the derivative of the original function, since we know how to do that already with quotient, product, whatever the rules, and now just plug and play to find the inverse. So in essence, to be honest with you, once we find the first three things, to find the inverse, the derivative of the inverse, it's just algebra. There's no calculus involved. The only calculus involved is finding the first derivative of the function. Example 3. F of x is equal to x cubed minus 2 for all x's greater than 0. Find the derivative of our inverse at x equals 6. We'll find it two ways, with and without the formula. Pause this right now. So to use the formula, what do we need to find? We need to have f of x, which we have that. We need to have f prime of x, which is that. We have to have the inverse, which we don't have yet. So we have to find the inverse. First step, switch x and y. And solve for y. So we have x plus 2 equals y cubed. Take the cube root of y. So my inverse is the cube root of x plus 2.
Which is taking the top of the side, since it's right in there.
Right. Well, I'm glad you asked that. The only time you ever take a plus or minus on a radical is if the root, the degree is even. Because if -2 cubed is going to be -8. +2 cubed is +8. So if it's an odd exponent, odd root, then it doesn't matter. But they just did that, just made it easier for us. Because in cube roots, you can't take cube roots of negative numbers. So now we gotta find the derivative of our inverse function. The derivative of our inverse function is, that's the function. F prime is 3x squared, so it's 3 f inverse squared. That's what that is. F inverse is 3 times the cube root of x plus 2 squared. Now, when x equals 6, the cube root of 6 plus 2 squared, the cube root of 8 . What is the cube root of 8?
2.
2. 3 times 4 is 1/12. So we have the derivative when x is 6, that equals 1/12. What would this one be? What information would go there?
12.
Because it's the opposite, this is slope. So what would the x value be to make it equal 12? What's our formula for f prime? Remember, was 3x squared. So where is 3x squared equal to 12?
2.
So we divide both sides by 3. X squared equals 4. Square root both sides. X equals plus or minus 2. Since we're only taking positives, so remember, we have to look at both sides. But what it really asked for was this. Without the formula, and this method is going to upset you even more because it's much faster. We want to know the derivative of the inverse. Remember, derivative is what? Finds what is the value of the derivative?
Slope.
The slope. So if we find the slope of the original function, and remember, the inverses are opposites. So what this is looking for at x equals 6, what it's saying back to the original equation, what this is saying is at what value does that equals the original function equals 6? Remember, in the original function, this is y and this is x. When we find the inverse, we had to switch x and y. So now this is the value y for this equation. This is the value x for the value. So at x cubed minus 2 equals 6, x cubed equals 8, cube root of both sides, x equals 2. So if I come over here and plug in 2, then I know that my derivative of my inverse function is simply the reciprocal of that. So in other words, in order to find the inverse, the derivative of the inverse, all you have to do is find the derivative of the original function at that value and then flip it. But this is the only part that's tricky right here. Because the x and y point here is actually the yx point here. Remember, first step of inverses, you have to switch x and y. That's the part that'll make you really mess up.
Is there problems where you can't use without the formula, or where like you could just use the formula and not allowed to use the formula without the formula?
Good question. Theoretically, I'd say no, you can do either way. Because if in order to find the inverse, you have to be given the original function. And if I give you the x and y point for the original function, I said when x equals, in this case, it was when x equals 2, if I gave you this and asked you to find the slope of the inverse, then it's just easy. Just find the slope of this equation when x equals 2. And then flip it. So theoretically, yes, I'd say no. I mean, either way you want to do could work. Good question. Now let's look at natural logs. Why do we pick natural logs? Because natural logs are inverses of what function?
Exponential.
Exponentials, right? And in engineering and biology and the sciences, exponential functions are very, 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 very important, very well, very widely used. So natural logs are the inverses. All right, so we're given this function, the original function. Because why am I doing this? Because this whole section deals with inverses. So right here, the formula to find the derivative of our inverse this is the formula we have to use. Start from here. Let's go. The first thing we have to find is what? Okay, we'll find the derivative. I was going to say we'll find the inverse, but yes, we use we use the derivative. The derivative of e to the x is so now we have our derivative, we have our inverse function, we can put them together. So the derivative of the inverse function is equal to 1 over f prime of x, where our x value is the inverse function. That's what this says. And our inverse function is ln x. There's another property. The two properties that we deal with a lot with exponentials if the bases are the same and they're the log base a of a or a log base of a, they both equal x. These are properties from algebra. So why do I say that? Because ln is the log base e. So since these are both log the same base e, our answer is 1 over x. Now, what is this? So what does this show us here? What do we just find right here? If we had to sum it up. What it's telling us is the inverse function derivative is that. So what that tells us is the derivative of our ln x dx is 1 over x. There is our derivative of our natural log function. Because of what we just found here. We can expand it even further now. ln of u. If y equals ln of u, what would y prime be? Well, it's a composite function. We use a chain rule. What's the derivative of ln? 1 over x. So here's our x. So it's 1 over u times the derivative of the inside, which is du dx. So this is the general formula for a derivative of an ln function. Are there any restrictions on x? For ln function? Not for this one. ln cannot be or in this case, u has to be greater than 0. Because the graph of ln looks like this. The y-axis is a vertical asymptote, which means it'll never get to it. Y equals ln of 2x. So what's the derivative of this using our formula? This should be in parentheses.
Would it be 1 over 2x times 2?
Very good. Because this is our u, so it's 1 over u, so it's 1 over 2x, times the derivative of u. Du is 2. The 2's cancel, so we get 1 over x. With that equation. Okay, the derivative. This is our u. So automatically it's 1 over u, which is x squared plus 3, times the derivative of u. The derivative of u is 2x. And there's our answer. What's our derivative? Straightforward? Y equals
Is it cosine over sine?
have you worked it out? Does it sound like a question instead of an answer?
It's the answer.
No.
No.
Cotangent?
Yes. This is u. So we need du. Derivative of sine is cosine. So the derivative of ln is 1 over u, which is 1 over sine x, times the derivative of sine x, which is cosine x, which makes it cosine over sine, which makes it cotangent. Remember last class, we talked about the derivative of u of absolute value of x. What is the derivative of absolute value of x? X over absolute value of x. Why? Because the formula we used was this one. And we took a derivative of this one using the chain rule. Anybody want me to go over that again? Okay. So if this is our function, then this could be rewritten as x squared to the power 1/2. So the outer function is 1/2. So I'll bring down the 1/2. Leave the inside alone. Subtract 1, so it's negative 1/2. Times the derivative of the inside, which is 2x. So it's 2x over 2 square root of x squared. The twos cancel. Square root of x squared is absolute value of x. So it's x absolute value of x. So the derivative, since it's ln, it's 1 over u, which is absolute value of x. The derivative of absolute value of x is x over absolute value of x. One times x is x. Absolute value of x times absolute value of x is what? Y. From this reasoning here. If we have absolute value of x times absolute value of x, that's a square root of x squared times square root of x squared, which makes it square root of x squared squared. Those cancel, leaving us with x squared. Which leaves us with a derivative of 1 over x. What do y'all think? Mind altering, scratchy foreheads, what?
It makes sense.
Yeah, once I write it down, it makes sense. But these last four, if I were just to give them to you by yourself, without any help. Yes, yeah, so, I mean, that's what, a lot of these formulas are usually just plug and play. We just have to know what to plug in there and what to play with. Like this last one, I doubt if any of you got that. Simply because of the concept of absolute value of x is square root of x squared. Most students will say, well, square root and x squared cancel out, so it's just x. No, it's not x, because if it was true, then it wouldn't be absolute value of x. It's its own function. Absolute value of x times absolute value of x. Most of y'all would just put absolute value of x squared. You have to relate it back to the original function. Because absolute value is one of the special functions that we deal with. And put it down to the basic functions that we always have to relate to. So the derivative of absolute value of x, or the absolute value of u, if it's some function, is 1 over x, 1 over u du dx. If you have a constant multiple to your variable, it's always going to be 1 over x. Can you guess why?
It gets canceled out whenever you find the derivative of.
Very good, yeah, because the derivative of ln is whatever this is. So it's 1 over ax times the derivative of ax is a, so they cancel. Very good. Example 4. A line with slope m passes through the origin and is tangent to the graph of y equals ln x. What is m? So let's begin looking at this. A line with a slope m passes through the origin and is tangent to the graph of ln x. Well, first off, what's the graph of ln x look like? It's an increasing function. Crosses through the value x equals 1. So there's a line going through the origin that has slope m and is tangent to the curve. So it touches it at one point. It touches it at one point down the line. Do we know what that point is? It's just some value a. Or we can put x, doesn't matter what we put in there. What's the y value of it? Because it's got to touch that curve. So in other words, at this point, the line and the curve both share the same point. What's the point on this curve? At A. This equation is what for this line, this curve? Ln x. So what x value am I touching it at? A. So if that's the case, then this has to have the point ln A. That's the y value of it. And it goes through the origin. So the slope of the line has to equal the slope of the curve. How do we find the slope of a line?
Derivative.
But we don't have the slope, we don't have the equation of a line.
From the slope of y or
Nope.
in x.
That's where they'll be equal, but we have to first find the equation for it. Slope of a line will we start
Oh,
off
y
course
x
with
mx plus
the
b.
slope equation. It's y2 minus y1
Mm.
x2 minus x1. the slope of the curve. The slope of the curve is the derivative of the curve, which is 1 over x. In general, as slope of any curve. So our first point is at 0, 0. This is x1, y1. This next point is x2, y2, and that's at point A, ln A. So y2 is ln A minus y1 is 0. X2 is A minus x1, which is 0. And at that point, it's 1 over A. So I want to know the slope at that point there, not the curve, but that point there. That's at point A. So far, so good? Again, we tend to, the further we get in a course, we tend to overthink things, try to make it has to be something that we just did. No, always go back to the basics. There's the slope of a line. That's y2 minus y1 over x1. All right, so back up there. So this gives us ln A over A equals 1 over A. We're in the process of solving for A. Multiply both sides by A. So we have ln A equals 1. So what is the value for A? How do we find the value for A? Well, how do we get rid of ln? What's the inverse of ln?
1 over A.
That's the derivative. The inverse is E. So we take the E of both sides. So E ln A is equal to E of 1. You get rid of an ln by E, or you get rid of a log by taking base A to both sides. So ln and E cancel, so we just have A is equal to E. Now, the slope of the curve is 1 over A. So the slope of the curve is 1 over A. Well, A is E, so the equation is 1 over E. So that just deals, we're just talking about exponentials and logarithmic equations. Now for any other base, and since it's no longer E, now we're taking log base A of U. To begin with, because now how do we relate this back to what we've been dealing with E and ln? A to the power x. A to the power x is the same thing as E to the power ln a to the power x. True? Because the e and the ln cancels, so we have ax equals ax. Now, since this is an exponent to an exponent, this exponent comes out in front. So that's e to the power x ln a. So a to the power x is the same thing as e x ln a. Why is that important? Because when we take the derivative of e x ln a, we only take a derivative with respect to x, so the ln a doesn't play any part to it. So the derivative of a to the x is the derivative of e x ln a. So what's the derivative of e x to ln a? Remember what the derivative, if y equals eu, what's the derivative of e to the power u?
U times e to the u.
Eu du, right. So in this case, u is the x ln a. So the derivative is e x ln a times the derivative of x ln a. The only derivative you take is x. What's the derivative of x? 1. So it's times ln a. Now, how does it relate to this? E x ln a is a to the power x times ln a. So the derivative of a to the power x is a to the power x ln a. Let's take an example here. If y is equal to 3x, what's the first derivative? We'll be using this.
Three to that, it's not three X.
It's 3 to the power x, right? Yeah, that'd be pretty boring if it was just 3 to the x. So it's, if I start off with this one, I still have 3. So I'll still have 3 to the power x. What is my value of a? A is the base. So the derivative is okay, here's a note. So I was looking at this one. What if we had a to the power u? The derivative of a to the power u would be au ln a times du dx. If your exponent isn't a constant, if it's a function. Why do I say that? Because this is a function. It's -1 times u. So we have a to the power u, which is 3 to the power -x, times ln, the base is 3, times, what's the derivative of the exponent? -1. So the answer is -3 x ln 3. So derivative here is the original equation, 3 sine x times ln, the base is 3, ln 3, times the derivative of sine, which is cosine. So it's 3 sine x ln 3 cosine x. So far, so good? Yes.
Number two, the reason it's -3 is essentially it's 3 different multiples, but you know, negative.
Well, we took a derivative, take the derivative of -x. -x is -1. So that's why it's just 3 times -1 is -3. Yeah, they're all multiplied together. So since if any one of them, if you're multiplied and any one of them negative, the answer is negative. What if we had, instead of ln, we had log base 8, where is it a log base 10? Remember, in algebra, we have 3 types of logarithms. We have the common log, we have the natural log, and then we have all other logs. What distinguishes them apart? The bases. Common log, the base is 10. Natural log, the base is e. And everything else, it is what it is. Now, if this is the case, then rewrite it in terms of ln or log base 10. Typically, ln's the easier one to deal with because they're log base e, and taking derivatives of e and ln are just much easier now. The most common question at this point is, how do we do that? So log base a of x is something called the change of base. You should learn this in algebra again. What the change of base does is it takes the log base of any number and rewrites them as a ratio of either natural logs or common logs. So whatever is the operation, that goes with the numerator. Whatever the base goes with the denominator. Or we can go with common logs. If you think about it, in your calculators, do you ever see, well, you may now with the new Fandango ones, but traditionally in calculators, you never see a log base A button anywhere. All you see, no, I can't find it on there. It's off this one. But all you'll see is either ln or log on a calculator. Which means if you have a log base whatever of number, you'll have to convert them to log base e or log base 10, ln or log. And that's how you do it. Because now you can use a calculator to do it. So if y equals log base a of x, then the derivative would be the first thing we would have to do is change this preferably to log base e, ln function. Because now we have to take a derivative of ln x over ln a. You see the simplicity of it now? The derivative with respect to x. Does a, is that a function of x? No, it's a constant. So we can bring that out in front even. So all we're looking for is the derivative of ln x. Because we're only taking derivatives with respect to x. So we have 1 over ln a. What's the derivative of ln x? We just talked about
Whatever
that.
x.
1 over x, thank you. So it's 1 over x ln a. That's the derivative of log base a of x. And in general, the derivative of log base A of u, so if it's a function, is equal to 1 over u ln A du dx times du dx. Find the derivative of log base 3 of 5x. Because since we have a u factor here, we use this equation. What is u? Out of this equation, what is u? Looking at this, what is,
5x.
yeah, it's 5x. So what would du be?
5,
What's a?
3.
It's the base. It's the base. Once you label these, the derivative is done. 1 over u. U is 5x. ln A. A is 3. Times du. Du is 5. So it's 5 over 5x ln 3. The 5's cancel, which is 1 over x ln 3. There's your answer. It's just a matter of plugging and playing. Given x squared plus 1 x plus 3 to the power 1/2 x minus 1. What I should have done is, instead of this one, I should just give it to you like this. Find y prime. Now, the first method I know is thinking through your head is you have to use the quotient rule, right? And then on top, you have to use the product rule with the chain rule with the second one. Yes, that wouldn't be wrong, but it would be very, 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 very labor intensive. There's a faster way of doing this. Using logarithms or natural logs. If we have this equation, if we took the ln of both sides, so what's the derivative of ln y? What's the derivative of ln x?
What over x?
Yeah, so derivative of ln y would
1
be,
over y.
but what else do we need?
dyx.
You need dy dx, because if whenever you take a derivative of y, it's an implicit differentiation, which means you have to take a dy dx afterwards. Okay, so that's the left side. On the right side, we can use the logarithmic properties. The properties of logarithms say this. If I have the product of two numbers or two terms, I can split those up. That's one property. Another property says if I take the quotient of two terms, I can split those up, but whatever's on the bottom gets a minus. And that's all because the bottom, if you bring it to the top, it has a negative exponent. Well, let me show you what this means. How are these are both exactly the same. Because ln A over B is the same thing as ln A times B to the power -1. Whenever you change location, you change the sign of the exponent. So I have ln A plus ln B to the power -1. Since you have an exponent, it goes out in front. So it becomes ln A minus ln B. That's where it comes from. Whenever you have an exponent, it goes out in front. That's a quick run through of the rules of logarithms. That's chapter 5 in algebra. So, using these properties, look at this. What this thing says, if it's on top, if it's multiplied, you add. If it's on the bottom, you put a negative sign in front of it. So what this says is I have ln x squared plus 1 plus ln square root of x plus 3 minus ln x minus 1. Because this is on the bottom, it gets a negative in front of it. Okay, so we have 1 over y dy dx is equal to ln x squared plus 1 plus ln, well, the square root, you can't have radicals inside there, so that becomes a power 1/2. So this radical can be rewritten as the power 1/2 minus 1. So now what do you do with exponents? According to this, if you have an exponent, it goes out in front. X squared plus 1. So this comes out here. So it's 1/2 ln x plus 3 minus ln x minus 1. No, notice we haven't taken the derivative of this side yet. All we've done is taken the derivative of this side. We're just rewriting this one. Now let's take a derivative of these. What's the derivative of ln x squared plus 1? Ln u is 1 over u du. So it's 1 over x squared plus 1 times the derivative of x squared plus 1 is 2x. Plus 1/2. Same thing here. 1 over x plus 3. The derivative of x plus 3 is 1 minus 1 over x minus 1 times the derivative of the inside, which is 1. Much easier, isn't it? It's really zero thinking. So we have 1 over y dy dx is equal to 2x over x squared plus 1 plus 1 over 2x plus 3 minus 1 over x minus 1. So far, so good?
Yes, sir.
Remember, we're looking for the derivative. The derivative is dy dx. So we have to get rid of this. How do we get rid of the 1 over y? To get rid of 1 over y, we multiply both sides by y. So those cancel. So our dy dx is equal to y times this whole thing I'll just go ahead and distribute that one. So it's 2x plus 6 on the bottom there. Now, what is y? Y
dy
is what we started off.
dx. Oh, okay.
Y is what we start off with. So the derivative is the original function. That was a good thought though, but no. X squared plus 1. I'll put this in parentheses. So it's x to the power 1/2 all over x minus 1 times this whole big thing. 2x x squared plus 1 plus 1 over 2x plus 6 minus that. And you were done. I wouldn't go any further. Why? Because if I give you a value of x, instead of multiplying everything together, just leave it like this and plug them in there in small numbers. So if I want to know the slope at x equals 2, If I wanted the slope at x equals 2, I would just plug in 2 inside all the x's and combine it all from there. I'd leave it like that. This is your derivative. Look for the next.
Is it possible to find a higher order derivative with this, for this?
Yes. But see, that's not what this was looking for. This is looking, well, I'll say yes, because now, if we started off with this equation here, and we found the first derivative is here, then for the second derivative, you would have to first, you'd have to distribute all those together. And that would be very painful. But yes, it's possible. Pretty much, there's no easy way around it. Because if you were looking for the second derivative, you can go ahead and try to do the product rule, which would suck. Or you can multiply this to each one of those and expand it using the ln function. You can do it again. You can take the ln of both sides again. But that would be very, 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 very arduous. Actually, let's look at this. Would it be that bad? Because since this is multiplied, we'd have the ln of this side plus the ln of this side. You see what I'm saying? And it wouldn't be so bad. We already know what this answer is. The ln of this one is all this. And then we take the ln of this one, which is just that. It's possible, very possible. But you'd be writing for a very long time. Actually, if that was a test question, I could only ask one question. If I gave you this and asked you to find the second derivative of it, it would take you an hour and a half about to do that. Because it took us about 20 minutes just to do this first part. That'd be cool. Oh, example 7. What would the first derivative of that one be? Well, think about it. Earlier, we had that. How did we rewrite that? Where is that? Right here. So this we said was the same thing as E ln a to the x, which was E x ln a. let's do the same thing with this one. So this can be rewritten as E ln x to the x, which is E x ln x. So let's take the derivative of this. To find the derivative, let's take the derivative of this function. So what's the derivative of E x ln x? E x ln x times the derivative of the exponent. The exponent's a product rule. We have x ln x, the derivative of x is 1. The derivative of ln x is 1 over x. So it's going to be ln x plus x times 1 over x is 1. So the derivative is E ln x is the same thing as x to the power x times ln x plus 1. So it works no matter what we have. So, any questions? You can leave anytime you want to. I mean, I'm not holding you. But if everybody else should stay, you stay. You ready for the in-class exam coming up?
What's the date on that?
Yes, I will. Any questions about this stuff?
No.
Mm,
End of section. Yeah, I mean, the concepts are pretty straightforward. If you think about it, the last 3 types of things we did are all the same format. It's just that numbers and letters have changed. You just have to know when they go and where to go. All right, everybody.